Let's do one more. N equals 4.
-8.5.
Negative 0.85?
-8. Oh, yeah.
Okay. Now, there's a couple things to notice about these. Notice, now again, remember, this is the electron that's happiest, so it's closest to the nucleus. This is the happiest it can get, the closest to the nucleus that it can get. These are less happy because they're further from the nucleus. Notice that the energy levels are getting closer and closer to each other. The energy levels keep getting closer and closer to each other. Now, theoretically, you could keep on doing this forever, till infinity. The energy levels would just keep on getting closer every time, until you kind of get to the top, where n equals infinity. If n equals infinity, what would the energy be?
0.
Right? And what does that mean? This is when you've just released the electron from the atom. So that would be ionizing the atom when you pull it away. So how much energy then does it take to ionize this hydrogen atom? How much energy does it take to get from here to here?
13.6.
Yeah, it would take, so if you put in 13.6 electron volts, you would put in so much energy that the electron would get all the way to infinity, which means that it's free. And then the electron would be free from the atom, and it would run off. And I think once the electron is free, its energy isn't quantized anymore. Once the electron is free, it can take on any energy. So what would happen if you put in, say, 14 electron volts? Would that be enough to ionize it?
Yeah.
Yeah. So this would take 13.6 electron volts and get up to here. And what would happen to the last 0.4 electron volts? Well, that would be left over, so that would be its kinetic energy. So it would be free, and it would be whizzing off with a kinetic energy of 0.4 electron volts. If you only put in 13.6 electron volts, then it's just barely getting free. So it gets out of the atom, but then it just kind of sits there. That's because it has no kinetic energy left over. So if you put in a small amount of energy, you can raise it to a higher level inside the atom, but it doesn't get free. But if you get it to n equals infinity, then its energy is 0, and then it's free. So when the electron is inside the atom, it has a negative energy, and when it's freed, it has a positive energy. That makes sense because remember, the electron wants to be in the atom, because that puts it next to the positive nucleus. So it's unhappy when it's freed, and it gives that a positive energy. All right, and again, this is showing that the energies are quantized. So this should seem kind of weird. Again, it would seem like the electron could be as close to the nucleus or as far from the nucleus as it wants. For example, if you've got, say, planets around the star, it seems like the planet could be as close to the star or as far as you want. But actually, on the microscopic scale here, there's only certain energy levels that are allowed. So that's our quantization. All right, a couple other points here. So what does EV a unit for? What concept is measured in EV?
Potential difference.
Now, that turns out not to be quite right, but I think what you're thinking of is volts.
Yeah.
Volts are a measure of potential difference. But these are not volts, they're electron volts. And electron volts are something different. Electron volts are a measure of energy. So this is important to make a note of. Volts are a unit of potential, but electron volts are a unit of energy. Electron volts are a very small unit of energy that might be useful when you're working on the atomic scale. Now, electron volts are definitely not the standard unit for energy. What was the SI standard unit for energy?
Joules.
So we need to know how to convert these, because a lot of times we can't use electron volts. We have to convert to standard units. These formulas up here, we need to be working with standard units, not electron volts, unless we take special precautions. So let's look at your conversions. What's the conversion between electron volts and
One
joules?
electron volt equals 1.6 O2 times 10 to the negative 8 joules.
Right, in your inside cover, you saw 1.6 electron volts. Oops, 1 electron volt equals 1.6 times 10 to the negative 19 joules. So that's something else that you want to lose. Very often we have to convert from electron volts into joules. And as I said, you can see the electron volt is a very small amount of energy. So it's appropriate when you're working on this atomic scale. Okay, so electron volts are a measure of energy, volts are a measure of potential. So let's say that I want to take an electron from here and move it up to here. I want to take an electron from this energy level and move it up to here. How am I going to do that? Do I have to put energy in or take energy out?
Take energy out. Don't put energy in.
Yeah, the electron doesn't want to go up here. I need to give it energy. Just like if the chalk holder starts on the table, I have to put energy in to raise it up. It doesn't want to go up automatically. Where's the energy going to come from? Well, it comes from shooting a photon at the atom. We're going to shoot a photon of electromagnetic energy here. And then do we want the electron to emit that photon or absorb it?
Absorb.
Because otherwise it wouldn't be getting the energy. We want it to get the energy from that photon by absorbing it. So the way to move up here is by absorbing a photon. Well, let's figure out what photon we would need. How much energy would it take to go from here to here? How can we figure out how much energy it takes to go from here to here?
3.4 minus 1.5.
Yes, say that again, sorry.
3.4 minus 1.5.
That's right. Or if you were going to use the negative signs, it would be negative 1.5 minus negative 3.4. But actually, yeah, maybe it's easier just to get rid of the signs. Okay. But you have to be careful with the signs here. That would tell you how much energy.
Yeah.
All right. But once you know how much energy, how do you use that to figure out what type of photon you're shooting?
You use E equals HF.
Good. Why aren't you using this down here? Because we're looking at a photon, right? We can't use this flowchart because we want to know the photon. So once we know the energy, we would use this. However, so what would we plug in for E?
3.4 minus 1.5.
There's a problem there. That's in electron volts. But remember, these formulas, if you're using the standard form of H, the standard form of H is in joules. So the first thing you'd have to do is convert your electron volts into joules. We don't have to do that right now. But anyway, you would convert into joules, and then that would give you the photon over here.
Okay.
Yeah, why don't we do that? So let's actually figure out that photon. So how much energy does it take to go from here to here?
1.9. So you divide that by 1.602.
Let's do that conversion on paper. So how would we convert this here?
1.9 electron volts
Right.
times 1.602 times 10 to the 19 joules per 1 electron.
Good. Why don't we just say 1.6? That's good enough. 1.6 here. So it sounded like maybe we're going to do a division here,
Yeah.
but what we want to do is multiply.
3.04 times 10 to the 19
And what are the units on that answer?
joules.
Yeah, the whole point was to translate into joules. Okay, why don't we finish off the problem now then? What would we do now?
That over 6.36 times 10 to the 34.
I think it's 6.63.
Oh, okay.
6.63 times 10 to the negative 34 is H. So now we're using this formula and plugging in for our energy.
So 4.6 times 10 to the 14th is your frequency.
Yeah, what would be the units on that?
Hertz.
Yeah, hertz. Good. Okay, what if they asked you for the wavelength?
Then you do C equals F.
Yeah, then you would use this, but we don't need to do that. But anyway, then we'd have to use this. All right, so this is a very popular type of question that you'll need on the homework, and you'll definitely have to do this on the exam as well. So as usual, it's really helpful to draw a picture of what's going on here. All right, and now this told us, this tells the photon that was absorbed or the photon that was emitted?
The photon that was absorbed.
Because you have to absorb to move from here to here. On the other hand, suppose we have an electron that starts here and moves here. The electron starts at n equals 4 and moves to n equals 2. How could you, so first of all, is that going to absorb a photon or emit one?
Emit.
Because it's losing energy. Where's that energy going to go? Conservation of energy says it has to go somewhere, so it gets bundled into a photon and sent packing. So this would lose that energy. How can we figure out what type of photon that would be? Let's just talk that through.
You do the same thing. You do 3.4 minus 0.85.
Good.
And then convert it to joules.
Can't forget to convert into joules. Good.
And then do E equals HF.
Good. Okay, good. Now, I made this a little easier than it should have been because on a real problem, you wouldn't already have had all these numbers calculated.
Oh, yeah.
Right? I gave you a head start here. On a real problem, you have to start by calculating these energies. Only once you calculate the energies can you figure out the change in the energy. So oftentimes, so notice that we need two different energies to figure out the energy change over here. We need the energy we're starting at and the energy we're going to. So you actually have to make this table. Remember, this particular table is only when z equals 1.